we have Alberto Castellano Mora, and he's going to tell us about IR UV mixing and the Swampland.
Yes, thank you. So first of all, let me check whether you can see if the slides are advancing or not.
Yep, looks like it's working.
Okay. So let me first start by thanking the organizers for keep on going with this amazing seminar series, and also for giving me the opportunity to speak here today. So in this talk, I will present some recent work done in collaboration with my supervisor, Luis Ibañez, and also with Alberto, who's a postdoc now in SRK. And it will be entirely based on this paper that we put on the archives by the end of last year. And as you can see, the main topic will be essentially IR UV mixing and in the context of the Swampland. So let me first start by giving some motivations on the ideas that will occupy us on the next 25 minutes or so. So traditionally, in theoretical physics, the common point of view was that indeed quantum gravity had posed an immense problem tackled with little guidance, in the sense that it seemed to have imprinted only a few traces on the physics governing nature below the Planck energy. So starting from the most well-established theoretical framework that we currently have, which is of course quantum field theory, and trying to combine any such d-dimensional effective field theory with purely quantum gravity effects, what we typically do is to parameterize such effects in terms of an infinite number of higher dimensional operators suppressed by the Planck energy. And this of course stems from the traditional perspective of the Wilsonian understanding of effective field theories, in which there's a natural scale separation between the UV physics and whatever theory that we arrive at after flowing deep into the IR. However, perhaps from a more modern point of view, there are indeed reasons to believe that this is not quite correct. So in particular, in our field, we know that the concept of the Swampland, the related Swampland conjectures, indeed break with this logic of naturalness and scale separation, since it holds essentially that the quantum gravity actually imposes non-trivial constraints on the IR physics. So, for example, from the perspective of string theory, we usually have duality symmetries, which in some cases map the light spectrum of the theory into the supermassive one and vice versa. And additionally, and also independently from string theory a priori, we also have black hole physics, which seems to indicate some intricate relations between the UV and the IR of whatever matter theory that we consider to be coupled to Einstein gravity. And among them, I would say that the most important ones would be the maximum information content of spacetime and the related entropy bounds. Now, you may ask, okay, but from the perspective of an effective field theorist, how can I parameterize such UV-IR correlations? Well, the first idea that may come into mind would be to do so in terms of an expression of the following sort, in which what we essentially have is an upper bound for the UV cutoff of our effective field theory, which depends both on the IR cutoff, which is essentially related to the size of the box upon which we are restricting our effective field theory, and also the d-dimensional Planck scale. And this constraint arises through this delta parameter here, which is a possibly model-dependent constant, which in any event should be smaller than 1 just for consistency. And let me say that despite its simple form, this expression here exhibits some of the important features that we would expect from any genuine Swampland constraint. Namely, if we, for example, we let this Planck scale go to infinity, and hence we decouple effectively gravity from the game, we wouldn't expect any kind of constraint as arising from quantum gravity. And indeed, this is what happens here. Whenever we send this Planck energy to infinity, we essentially get no restriction at all. So there is no upper bound for local quantum field theory. So this is a very nice feature of this simple parameterization. As an outline, I'll first give some introduction on the formal ideas of this UV-IR mixing and what is the line of reasoning that we follow in our work. Then I'll discuss a small subtlety regarding the possible appearance of multiple towers and how one should make sense of this and try to compute the species scale in these complicated scenarios. And the bulk of the talk will focus on the holographic arguments themselves, which motivate this kind of UV-IR mixing, and their applications in the context of both anti-de Sitter and de Sitter backgrounds. So notice that these kind of genuine UV-IR mixing relations that we're trying to motivate here are not just purely academic, in the sense that they can lead to potentially measurable corrections or even consequences for physical observables. For example, you may think of, they naturally appear in loop computations in any effective field theory that you may work with, such as, for example, the standard model, and so on. And despite their simplicity, the simplicity of the expression that I was showing to you before, we will see that these quantitative relations may be motivated very precisely by holographic and entropic arguments. In particular, starting by the covariant entropy bound. Now, I should also say that these ideas are not entirely new. There were indeed old approaches dating back to this seminal work by Cohen, Kaplan, and Nelson in 1999, and more recent ones by Banks and collaborators, in which essentially they tried to use these holographic arguments to limit the applicability of quantum field theory applied to cosmologically large scales. Now, in a second step, by arguing that indeed the appropriate UV scale that would be entered in all these kind of UV-IR mixing relations should be taken as the fundamental quantum gravity scale, which should be indeed identified as the species scale, we will explain how these considerations lead naturally to the appearance of infinite tower of states, as typically happens in the Swampland context, such as, for example, when referring to the distance conjecture. Of course, life isn't always that easy, and we will see that there are very frequent instances in which we happen to find not only just one, but multiple towers getting asymptotically light, such as ones arising from KK replicas or even string excitation modes. And in these cases, it is not entirely clear to which towers are the Swampland conjectures referring, or even how should one make sense of the species scale itself? Which are the states of the species that should be taken into account in this computation? But in any event, we'll find that after taking all these subtleties into account, we will be able to rewrite these relations involving both the UV and the IR cutoffs in an expression which involves now the characteristic scales that enter into the definition or computation of the species scale, and we will recover an expression of this sort in which alpha d, as we will see, will be precisely determined in terms of the space-time dimension, and also captures some information about the fine structure of the towers. And notice how remarkable is that this expression indeed resembles the original formulation of the anti-de Sitter distance conjecture as proposed almost 3 years ago by these people. So it is natural to ask whether there is a way to phrase things in such a context such that this mere analogy may be lifted to a precise statement in which we can recover the ADS distance conjecture. And the answer turns out to be yes. Indeed, by identifying the inverse of the IR cutoff, namely the size of the box upon which we restrict our effective field theory with the ADS radius, we will see that we recover exactly the statement of the ADS distance conjecture. And not only that, because moreover, we will see how we can give or provide for both lower and upper bounds for the relevant parameter that enters into the computation, which in the end, and in the end, we'll see that this translates into the possibility, at least from this naive perspective, of a scale separation, which is something that in the strong versions of the original conjecture was proposed to be forbidden. But before delving into the unexpected consequences of having such a UV-IR mixing, let me comment a little bit about the UV cutoff. How should we make sense of it? So this scale should be taken as that one beyond which quantum gravity effects, pure quantum gravity effects, can no longer be ignored, and hence quantum field theory is not suitable anymore. And as such, it is typically argued that such a cutoff should be identified with a species scale, as introduced by Dwali quite a while ago. And this scale is usually defined, well, can be defined in any d-dimensional effective field theory weakly coupled to instant gravity by this expression here, in which this quantity essentially counts the number of distinguishable fields or degrees of freedom that happen to fall below the species scale itself. So a simple scheme would be this one here, in which we have some scale for the masses of the light fields, any other dimensionful coupling constant that we happen to have in our effective field theory, and on top of everything, both the species scale and the Planck scale. Now, what is important to us here is that typically in string theory compactifications in which we claim to have perturbative control, both either on the alpha prime expansion or even on the loop expansion, string coupling, what usually happens is that we get not only just one, but many tower of states as arising from KK states, BPS states from wrapped brains, or even string towers. So it's natural to ask in these more complicated setups, what is supposed to be the species scale? In other words, which species should I count in order to compute it? It's not clear at all. It's not obvious. Now, what is typically argued in the literature is that, at least for the purposes of determining this UV, this species bound, and so on, it is enough to focus just on the lightest tower. And usually, the Swampland conjectures, which refer in some way or another to this kind of infinite tower of states, typically are formulated with respect to these lightest towers. But the idea that the question that we want to address here is that indeed this is not always the case. So these naive expectations can fail. So we'll see how now. So in order to both set the notation that we'll use throughout the talk, the rest of the talk, and also for showing how these expectations can indeed fail, let me just consider two different scenarios. So in the first case, imagine that we happen to have just one tower, getting asymptotically light in Planck units, with an spectrum of this form, in which n is a natural number labeling the step of the tower, and p is what we call a density parameter, which essentially gives you what is the mass gap between the different steps in the tower. So in the simplest case, for p equals 1 on KK-like towers, we would simply have a mass gap given essentially by the scale of the tower. Now, more generally, this density parameter can be thought of as heuristically counting the number of KK towers which appear with the same mass gap. So, for example, imagine that we have two different KK towers. In each step, then we find two different states as coming from either one or the other tower, right? But for the purposes of counting the states and determining the entropy and so on, what we want to say is that this situation is equivalent to just rearrange things such that in the end what we have is just an effective tower with just one state per step, but of course with a smaller gap. So notice that I'm not saying that these two situations are physically equivalent. They're not. I mean, the spectrum are not the same. They have different masses, but just for the purposes of counting states and determining the species scale, they are. And indeed, one can argue that this is the most natural approach from the perspective of an effective field theory observer. Now, what happens if we have two different towers with, in principle, different spectrum, different density parameters, and so on and so forth? So in this case, the situation is more complicated. First, because apart from the states arising as from the first tower or the second tower, we typically have states which are mixed in the sense that they present charges with respect to the two towers at the same time. So you can think of it as, for example, states with non-trivial momenta along different internal directions of your compact space, in the case in which the towers are of KK nature, or even a string oscillator modes with non-trivial KK momenta. So in this case, one can repeat the question and ask ourselves, what is supposed to be the species scale? How should I count it? Well, there are essentially two possibilities. The first one is the most simple one, in which the two towers scale asymptotically in the same way. So it's fairly clear that we are essentially effectively back to this case that I was discussing here, in which we can rearrange things at the end by defining an effective tower with an effective scale, an effective density parameter, so on and so forth. But if one wants to do things more carefully, one can indeed count the number of lattice sites that fall below such species scale and conclude in the end that our expectations are indeed matched. Now, the most important case happens whenever this ratio between the two towers is indeed allowed to diverge. So that meaning that what we have is essentially parametric decoupling between the two towers. So even though both of them are getting light asymptotically, they're doing so at different rates. Now, as I was telling you before, intuitively, what one says is that since one can always make this ratio between the scales of the towers sufficiently large, meaning that we can go deep enough into the asymptotic regime, what one can do essentially is place as many excitations of the first tower below the first excited state of the second tower, so that it's reasonable to expect that in order to compute the species scale or to count states and so on, it should be just enough to focus on the state's charge under only the first tower. Now, the idea that we want to convey here is that this is not always the case, and this reasoning here above can fail sometimes. How can it fail? Well, imagine that you happen to compute the UV scale associated to the lightest tower, and you find it to be parametrically above the second tower. This would mean that even though this scale, of course, is going asymptotically to zero, the number of excited states of the second tower that nevertheless fall below such UV scale is indeed diverging, so that one cannot simply forget about them. And at the end of the day, physically what this is telling us is that is giving us important information about what should be the resolution of the infinite distance singularity from the perspective of quantum gravity. So, for example, this would be telling us things such that in some cases it wouldn't be enough just to decompactify the fastest growing cycle in order to resolve the singularity, but it may be required to further decompactify a second one, or things like that. I should also say that, of course, in the paper we give a general algorithm to compute this species scale in the more general setup in which there are n towers with n arbitrary becoming relevant. And we define these characteristic scales or effective towers and all their properties. So this is kind of the notation that we will use for the rest of the talk. Now let me go now into the details of the argument of the UV-IR mixing itself. So the argument of the UV-IR mixing that we give in the paper is entirely based on the covariant entropy bound, which was proposed by Busso in 1999 as a refinement of previous related ideas. And it states essentially that there is a maximum information content on any prescribed region of spacetime, which is given essentially by the entropy that would be associated to a black hole that just fits within such a prescribed region. Notice that from our quantum field theory experience, we know that by almost construction, the entropy is an extensive quantity, meaning that it grows like the volume over which it is defined. But as I'm saying here, quantum gravity, indeed, what it's telling us is that it requires the entropy to grow at most like the surface. So naively, it seems that this kind of constraint can indeed impose some restrictions for the validity of any effective field theory that we may happen to be used to describe some phenomena. So these considerations have been, of course, fairly general. So let me just put all these words into a more concrete scenario. So imagine that we start from a d-dimensional effective field theory with an UV cutoff, lambda UV, and lying in a spherical box of physical size L. Then the maximal possible field theoretical entropy will be captured by this formula here, which of course you can see is an extensive quantity. It grows like the volume. You may understand intuitively this relation by thinking about the effective field theory by thinking of it as effectively counting the number of oscillators that fit within some box of size given by the IR cutoff, and with a lattice with a spacing given essentially by the inverse of the UV cutoff, since we cannot resolve as distances smaller than this size here. However, as I'm stressing, quantum gravity requires this maximum entropy to grow not like the volume, but like the surface, so that intuitively, just by comparing these two quantities here, it seems reasonable that, and also by requiring that we do not overcount the number of available degrees of freedom as starting from the effective field theory, it seems reasonable that we would expect in the end to obtain such kind of relation between the UV cutoff and the IR cutoff. And this is precisely what happens here. This is the relation that we obtain. And if you remember, it's of the very same form as the one that I wrote for you at the beginning of the talk, in which now the delta parameter, which was left free there, can be seen to depend very precisely with respect to the space-time dimension of the field theory. Now, let me just stress once again that, of course, this kind of UV-IR correlations can lead to potentially measurable corrections. And this is something that was already investigated since the very beginning, and even more recently by the same people, in light of the recent experimental measurements with respect to the G-2 factors, or even for trying to extract some corrections for the cosmological constant itself, and so on. But in any event, what is important from this kind of argument relation is that it is a purely quantum gravity effect. So that if we, for example, take the limit in which this IR cutoff is going to 0, meaning that we enlarge our box indeed to infinity, the effective field theory completely breaks down. And why is that so? Well, simply because the UV cutoff is enforced to go all the way down to 0. So from our experience in string theory compactifications, we know that such a dramatic breakdown of the effective field theory cannot indeed be accomplished by a finite number of states. And it usually happens that this is forced on us by the appearance of infinite tower of states. So it's fairly natural to assume that this would be the way in which the effective field theory breaks down. And also for another perspective, but of course related in a sense, recall that I was stressing that since this is a purely quantum gravity effect, it is natural to identify the UV cutoff with the fundamental quantum gravity scale, which is the species scale. And hence, the fact that by taking this limit, we are forced to take the UV cutoff essentially to 0. This translates to an equivalent statement on a diverging number of species. Notice also that by recalling our discussion of the second part, in which we showed how the species scale indeed depends crucially on quantities that define the effective tower of states that are involved into its computation. And by trying to rewrite this expression here in terms of quantities that involve some characteristic scales of the tower, we arrived at the end of the day with an expression that this was of the form anticipated, which now the constraint applies not to the UV cutoff itself, but to the characteristic scale of the tower that is responsible for the breakdown. And this alpha d parameter can now be seen to depend crucially on the space-time dimension, and also to the density parameter, for example, of the tower of states. And more importantly, some nice feature of our argument is that it also provides for some lower bounds and upper bound for the maximum scale separation between the tower scale and the IR cutoff, which is these are the two quantities indeed that one arrives at, and they can be given physical sense by considering different tower spectrum becoming relevant. In any event, what is important here is, and it's something that I won't have enough time to discuss, but of course you can have a look at the paper or even ask me at the end of the talk, is that there is an important subtlety which has to do with the gravitational stability of the effective field theory itself. But this is something, of course, that was already taken into account in the first works. And what is important is that at the end of the day, it seems to lead to similar predictions, similar restrictions on the UV cutoff, and also but with, of course, different values for this alpha parameter. Now, you may notice that up to now, the IR cutoff has left arbitrary. I have not fixed it to any value at all. But whenever one considers curved backgrounds, for example, anti-Sitter or the Sitter spacetimes, there is a natural choice. So let me consider first the case of an effective field theory living on an ADS background, with ADS length related, of course, to the cosmological constant. Then if we want to apply the same logic as we did before and try to see whether we can find some constraints for any effective field theory restricted to some region of this spacetime, we should start from the covariant entropy bound, which I have written for you once again here. How should we choose these regions? Well, we should choose them so that they give us relevant or interesting constraints. So in the paper, we argue that indeed, by taking spherical regions of proper constant radius in ADS, of a size given precisely by the same order of the ADS radius, we obtain the most interesting constraints. So you may argue, of course, it is perfectly possible to take spherical regions which are much bigger than the ADS radius or much smaller. But as we discuss on the paper, they do not lead to interesting restrictions, basically, either because the ADS geometry fixes itself in the sense that, for example, for big values of the spheres, the volume and the area grows at the same rate, or even because by taking small boxes, we lose any information about the curvature, and we are effectively back in Minkowski, so that we cannot say anything at all about non-trivial curvature of the spacetime. In any event, by applying the same logic as before and running exactly the same arguments, we arrive at the same formula. But of course, in this case, in an entirely different context, where now this IR cutoff should be identified with the cosmological constant. So that indeed, by taking the limit in which this cosmological constant goes to 0 in Planck units, we are forced to recover or to recover a complete breakdown of the effective field theory as produced by an infinite tower of states. And if you remember, this is essentially the same statement as the anti-de Sitter distance conjecture as originally proposed. But the important our holographic arguments are indeed a priori independent of string theory. So that it may tell us what goes wrong in quantum gravity terms, which is something that was still missing in the original conjecture.
Just to say, Alberto, you're starting to eat into your question time.
Okay, so let me just finish in a couple of minutes. Very
sure,
quickly.
No problem.
Okay, so of course we shouldn't stop here. We can extract much more information, but let me just summarize it very quickly. There is an interesting case in which we have just a single KK tower, as in the typical examples that are used as evidence for the strong version of the ADS distance conjecture, in which by substitution here in our family, we get essentially the same interval as the strong version, in which of course scale separation wouldn't be allowed. But from our perspective, this seems, or this suggests itself to be a kind of a mirage of the simplicity of the setup, in which we happen to have just only one tower. As long as we encounter some more complicated situations with different spectrum of light towers, in principle, values as more than 1/2 for this alpha parameter are allowed. So in principle, at least naively from this perspective, scale separation is not completely ruled out, in contrast with the original formulation of the conjecture. And one can also, for example, try to see if the examples that we know that are in the literature which exhibit this scale separation are indeed okay or not with our bounds. And as we analyze in the paper, they are, such as, for example, this DJKT example. One can repeat the same considerations, but for the Sitter vacua. In this case, there is a stronger notion of entropy bound, since it presents a universal upper bound due to the appearance of cosmological horizons for any observer. But the kind of relation or restrictions that we arrived at after running the arguments are essentially the same as in the Sitter case. But of course, there's an important subtlety that one has to take into account here, because unitarity in the Sitter requires, in the form of the Higuchi bound, to actually have scale separation. So it is remarkable how, from our simple holographic arguments, we can indeed reproduce smaller values for the alpha, smaller than 1/2, and indeed compatible with the scale separation, which is required, at least from this perspective, in the Sitter case. Right? Of course, this requires for a more complicated spectrum of towers, which is something that matches with our expectations, since we have these no-go theorems in which tell us that, for example, there's no possibility of having the Sitter as arising from just a single sphere compactification, so on and so forth. And just as an outlook, let me just briefly comment that one can try to apply these same arguments, but for the observed universe, for example, try to identify the IR cutoff with the cosmological constant, to obtain this rather small value for the UV cutoff, way smaller than the ones that we know that are at work in the, for example, standard model. But there's also another interesting possibility in which we identify we take the IR cutoff such that it essentially amounts to take a box with the small entire standard model fits into, which it translates into the statement of having a size of the box of the order of the inverse mass of the lightest neutrino. So I'll just leave here some points for future work. I won't read it so that you can, if you want, make any questions. But I'll leave it here so that you can write for yourselves some interesting questions left for future talk. So thank you.
Thanks a lot, Alberto. Very nice talk. So we have time for one very quick question, if there is, from the audience. Just raise your hand or unmute your mic.
Okay. Hi, I can't.
Yeah, go ahead.
I can't raise my hand. what happens if in pure Minkowski, strictly Minkowski, can you identify an IR cutoff or?
Yeah, the thing that what this is telling us is that if you want to do quantum field theory to like extend it to all Minkowski, that's not possible. That's at odds with the entropy one. You're somehow overcounting. Of course, I mean this is not telling us that there's something wrong. It's just that, of course, quantum field theory is not the fundamental framework in which to formulate quantum gravity. So, but it's not. So, in the end, if you, for example, start from type to be, I don't know, 10D supergravities, the kind of IR cutoffs that you find are not problematic. That's or these kind of relations or constraints are not problematic. They're perfectly well in the sense of the hierarchy that you get with respect to, for example, the string scale and this kind of stuff. So everything is perfect, at least from this perspective, in Minkowski, in, for example, 10 dimensions or 11 dimensions. This is not telling you that there's something fundamentally wrong. It's just that you wouldn't expect to be able to apply to an infinite trivial background this quantum field theory formalism. Anything but that.
Okay, thank you.
Well, thanks a lot, Alberto. Let's thank Alberto again.